quickly I'll try to speak slowly for our translators. Okay. So, yes, I've been working with Voith Turbo most of my professional career. It has all been related to mining applications. That's our core business, even though we do get involved with drive systems on many applications in steel, oil and gas, a lot of other industries. But my particular area of responsibility has pretty much always been focused on mining. So I had the opportunity to present to you probably the largest project Voith has ever done in material handling in my career, and the project is actually being installed right now and will be commissioned in the next 2 months. So you'll be able to see it. I'll reference it. Perfect. So the title of the project is Atlas Energy, and they previously were called Atlas Sand, and the project is Dune Express. And what that project is, by the way, it's terrible to present at this time after lunch, so there is going to be a test. So hopefully you can stay awake. A few questions, so be paying attention as we go through the project. Okay. So my agenda for today, we'll do a little bit of an introduction, then look at the particular drive technology that we applied on this project, and look at our worldwide installations, then get into the details on this particular project called Atlas Energy. We'll look at the scope and history, some of the key challenges we had for designing and supplying that system, and look at some details on the drive package itself. And then finally, there's a link. You can, Atlas Energy on their website, every few weeks updates a big video so you can see the progress of this project. So if you look at Atlas Energy Dune Express, you can get a lot more information than I will be able to present in the time frame here today. Okay, the main drives of Voith, most people in mining know Voith for our fluid couplings, or hydrodynamic couplings, we call them. And that has probably been our core product for many years. But in my 35 years career with Voith, we have expanded into many other products and technologies that we offer the mining industry. But most people are probably familiar with us relating to our constant fill, and this is a fill control fluid coupling, essentially like a liquid clutch. Okay, so the fill control couplings, the first series of fill control couplings Voith developed in 1997. I was part of that development, and that was called the TPKL. And this series is now called the TPXL, and the main reason for the new series is we developed a very special internal profile that has twice the torque capacity for the same diameter runner. So we took advantage of that new technology and generated an entirely new line of fill control couplings. These are applied typically to larger, higher power conveyors, higher mass conveyors, and we apply these when a constant fill coupling is not able to handle the acceleration and operation of a bigger drive. So we first try to put a constant fill because that's the most economical coupling we can provide, but when the application requirements go beyond that, then we look at an actively controlled coupling that has a sump in the bottom. Oil stays in the bottom, it has an active pump, and we control oil filling into the coupling and out of the coupling. So with that, with a PLC control, we have very good control of the torque and speed that we are applying to a conveyor. So it's quite compact. The unit you're looking at there is rated at about 300 to 500 kilowatt. And that's one of the smaller units. We go up to about 3 megawatt per drive in this series of coupling. So to control it, we developed our own controller, and one controller, it's called the turbo belt drive controller. That controller is capable of up to 8 drives, controlling up to 8. Now you say, when do you ever see that? Well, I've been involved in several conveyors that had many drives, as many as 7. In the particular project Atlas that we're going to be looking at, there are 3 conveyors that have these fill control couplings, the 3 longest conveyors on this overland system. One has 4 drives, one has 5, and the last one has 6. So this controller controls all of those simultaneously for one drive to give us active load sharing and a very long controlled acceleration. Okay? So that is part, when we supply this drive, it is a fully, as close to plug and play as you can get. All the software has already been developed, and it's in there, and it can be, parameters can be set up for each conveyor, but all the smarts for controlling that conveyor are already in there. We do not have to redevelop that every time we have a different application. We can communicate via internet. If the customer allows us, if we ever have software updates or anything like that, we can actually, via cell phone or fiber optic connectivity to the internet, we can actually download software, update programs, and do that kind of thing. But normally that controller is standalone and is not communicating with the cloud or anything else. So some of the features that we highlight with the turbo belt drive controller, again, it's a fully developed control logic. It's flexible communication. It has various different ways to communicate with the main control system of the mine. One of the things that's very unique with this controller is we have slip detection and correction. So when you're driving a pulley on a belt conveyor, there are times maybe there's water on the belt, or the tension isn't correct in the tensioning unit, and the pulley begins to slip. We actually sense that, and we intervene if we see the pulley beginning to slip. There were some pictures of fire just before, some of our colleagues. Well, that's the result. If you allow a pulley to slip very long on a belt conveyor, you'll have a fire. So we want to intervene before that happens, so we monitor. And if we see that slipping, it means we're trying to put too much torque into that pulley. We back fluid out of the coupling, let the pulley re-grip, and then try to load share and bring the torque back up. Active load sharing is equal or proportional. So on the Atlas project, let's say the one conveyor has 6 drives. One way to control that is just have even load sharing with all 6 drives. There are design reasons why that is not necessarily always the best. You might want to have more torque, on one pulley and less on another. So the program is set up that you can actually select whether you want even load sharing or what we call proportional load sharing, maybe 60% on this pulley, 40% on that pulley. So it's fully adjustable for that. Atlas has 2 of the drives, we'll see very shortly. 2 of the conveyors are the 2 longest conveyors in the world without an intermediate drive. So they have most of the drives at the head end of the conveyor, and they have a single drive at the tail end of the conveyor. Because that conveyor is so long, one is 23 kilometers, the other is 26 kilometers. Because it's that long, we have to have a drive at the tail, just bringing the return belt along the bottom side of the conveyor. And that is controlled not by load sharing, but tension control of the belt at the tail. So a very unique way to control that. The tail drive does not care what the head drives are doing. It's totally independent. And the torque we apply at the tail is based on maintaining a very accurate tension at the tail. The 2 biggest conveyors I mentioned have horizontal curves, so they're not straight. And that's really critical to have very good torque control when the belt is going around a big sweeping turn, and they have several on those conveyors. All right. We also have the ability, if there's a maintenance issue or one drive needs to go off, that you can deselect the drive and continue to run. This shows the power range of the turbo belt. As you can see, we have 5 sizes from 315 up to 2500. And this really means the power rating in kilowatts at 1500 RPM. Now, I do want to make a comment because I know there's like Vale, very strong-minded about 900 RPM, and there's a big history with that. But all of our field control couplings, I've done 500 in the US, they're all running at 1800. Elsewhere in the world, we're at 1500 RPM, 50 hertz power. There's over 1,500 field control couplings in operation. So the rest of the mining world uses 4-pole motor speed for the drives. And with a fluid coupling, the slower the motor, the bigger the coupling has to get, as you can see on this chart. So assuming 1,800, which would be available here in Brazil, we can do up to 2.5 megawatt per drive. So if you had, say, 4 drives, that's a 10 megawatt conveyor. So we're not limited. We can pretty well apply this technology to virtually any conveyor that the mining industry can throw at us. So the new turbo belt, these are the current installations that are going in. The Atlas is going to be 21 in the US, but this is growing very rapidly now as this technology is catching on and customers are seeing how well this works. Okay, now we'll get into the details of the Dune Express overland conveyor system. So if any of you are familiar with a map of the US, Texas is there on your right, New Mexico on your left, and Mexico here across the border with the Rio Grande. So in the US, the biggest source of oil, just like you have Petrobras, okay? Biggest source of oil, Petrobras is drilling out in the ocean. We have the oil in underground shale. It's called shale oil. So we have to drill down 2,000 to 3,000 meters and then go horizontal in the shale to get that oil out of the shale, okay? That area, the gray area you see, is as big as some of the states in Brazil. It's huge, and it's all shale. So 2/3 of all the oil in the US being produced right now is coming out of this area of Texas and New Mexico. It's called the Permian Basin. And some details about how much oil and natural gas are coming out of that Permian Basin. I was just there 2 weeks, and when you drive out there, it's very flat. You see nothing but oil rigs everywhere. You can't look and not see 100 oil rigs going. The area has wells totally everywhere that you can imagine in that area. So Atlas Sand owns a big sand pit called the Kermit Sand Pit right at the end of that arrow, which is strategically located right in the middle of the Permian Basin, so very good for them. They don't have to ship oil or sand very far. So Atlas is producing sand, and this conveyor is hauling sand. And people think, wow, big conveyor with sand, why? Well, sand is used in the fracking process. So here we showed, this is in feet, 7,000 feet. You drill down, then you drill horizontally. And this could be the distance from here to the end, could be 2 or 3 kilometers drilling. And then you frack it, okay? You put high pressure water with sand down the well because you want to crack the shale, and then the sand holds the cracks open while the oil and gas flow back into the well. Okay, so that's the fracking process. Each well takes 10,000 tons of sand. So there's a huge market for sand. And in that area of Texas, if we go back 2 slides, it is the most dangerous road in the US for accidents because there's nothing but truck traffic, heavy truck traffic going over 100 miles an hour to get the sand from the sand pit to the wells. So this project for Atlas Sand, believe it or not, it's a $400 million project. It is the largest material handling project in the world in the last 40 years, plus. And the main reason was insurance costs. Atlas has to pay very high insurance costs to keep their trucks on the road delivering sand. So they came up with this idea that if they use a conveyor and take the sand as far away as they can get closer to the wells, they can only use the trucks for the last distance hauling to the well, but the conveyor will take the sand 70 kilometers. So the Atlas Overland is 70 kilometers long. To give you an idea, that is the second longest overland system in the world and the longest in North and South America. Okay, so there's a Google Maps view. The very short little hook on the end that you see the Kermit sand pit on the right, and that very short section is conveyor 1. Then the rest of the distance is conveyor CV2, 3, and 4. And that total length is 70 kilometers in length. And what this does is eliminate 200 kilometers of truck haulage by them putting this sand on this conveyor and moving it. And this conveyor system is actually designed to offload right at the Texas-New Mexico border. There's an offload station, and they also have mobile off. They can go anywhere that they can get a truck along that, and they can put a mobile offload station to fill up a truck, or many trucks, and do that. So it's the most engineered and instrumented conveyor system in the world. Everything is instrumented. Everything will be monitored remotely from their headquarters in Texas, which is 1,200 miles away. Because you can imagine, you just can't possibly have to monitor the system. So they are using smart idlers. Every idler on the conveyor, 63,000 idlers, has active wireless sensors in it, sending RPM, temperature, and vibration. So they will know the condition of every single idler on that conveyor. And again, 63,000 idlers. And they'll be able to then draw maintenance attention to their maintenance crew. Hey, you have to go to this station and get those idlers. They've even designed a conveyor that they can act while the conveyor's running. They have a machine that will pick the belt up, pull the bad idlers out, put the new idlers back in, drop the conveyor back on the fly, never stopping the conveyor. So a lot of new technologies are built into this conveyor. So here's the details for the 4 conveyors. First 1.5 kilometers, second one 24. Remember the test? The end of third one almost 16 kilometers, and the last one 26.3. So CV2 and 4, as I said, will be the longest conveyors in the world without an intermediate dry tail and head. So setting 2 world records. That is the Atlas. That is at the Kermit sand pit where this conveyor was started. So when it comes to designing very long overland conveyors, and especially conveyors with horizontal curves, you have to engage some very knowledgeable and experienced companies that are renowned in the world to do that. Atlas hired Conveyor Dynamics to do that. They're based out of the state of Washington in the US. And they're one of the first companies that developed a software to digitally model a conveyor system. And they were responsible for the complete design of the overland. So Conveyor Dynamics designed it, but they don't build. They're not a manufacturer, so they don't actually fabricate any steel. Atlas had all that steel fabricated according to Conveyor Dynamics. But before we got that far in building it, Atlas Sand wanted Conveyor Dynamics to prove with their program that whatever system they were going to use to start this was going to work and not cause a problem. Well, people don't know this, but Voith, we have the same capability. It's not something we advertise, but it's part of our conveyor consulting capabilities that we can do. And when Atlas found out that we can do it as well, they said, great. We want you and Conveyor Dynamics to work together. You do your model, they do their model, and you're going to compare results, and let's see what we find. And so The difference between our modeling effort is we actually have the software for the fill control coupling built into our dynamic model. So it's much more accurate than their model. Their model just assumed a certain torque buildup and maintained a certain torque and then looked at the results of the model. Ours actually used the controller that we're using for the fill control coupling. We have the fill versus slip curves and everything built into the model. So what was the result? On the top half, that was conveyor dynamics model. The blue line are all the drives at the head end of the conveyor. The pink or magenta line is the tail drive torque, and then you see the acceleration. If you note, what's the acceleration time? Can you see it?
10 minutes.
10 minutes, exactly. That was the big challenge for us. When I got this call, we'll just back up a second just so you know the history. In 2021, I get a call from a gentleman never knew, and he said, can you sell me a coupling that'll give me a 10-minute acceleration of a belt? And I'm like, well, I've never done that before. That's really, really long. A typical belt, 1 to 2 minutes, considered a very long, slow start, gentle start. 10 minutes is kind of out of this world. Most people would choose a frequency drive to do a 10 minutes. Most people would never consider a fluid coupling. The reason the project manager wanted a fluid coupling is he had 25 years of experience in Australia, and his most recent was in Mongolia. He had 2 overland conveyors with Voith fill control couplings in the mine. It was Outubro mine in Australia. Every other conveyor in the mine, and that was like 90% of the mine, was variable frequency drives on the rest of the conveyors. And he said he had nothing but trouble every day trying to keep the frequency drives running and keeping those conveyors running, and he never touched the Voith drives in 5 years. So he called us and said, if you could do it, I won't consider frequency drive at all for this project. But that time is really long. So this is really for us the first time we can prove that you can do something like that, even with a fluid coupling and in a very manner. So here our bottom curve, you can see how close the actual profile, the acceleration profile is, but we're even smoother as far as the torque response than what conveyor dynamics showed, because we have the real control algorithm for the coupling as part of the dynamic model. So with that, Atlas was happy that we're moving forward. We'll use the couplings, and then we went into the design phase of it. So part of the dynamics, what you want to be careful of is tension. And so what this is if you stretch the conveyor out to the end, the drives are in the middle, and this is the tension buildup. You can see we're 200 some seconds into a 600 second start. So this is the response of the conveyor in a dynamic model, and you don't want to go crazy. And it's very possible and easy if you don't apply the torque gently enough. Just like a rope, if I have a rope stretched out across the floor and I snap that rope, that wave will run down the rope, okay? That's a dynamic wave. The belt is exactly the same thing. If you apply torque too quick, you will send a tension wave traveling down that belt. And when it gets to the other end, it can break things. It can get really, really ugly, and you can destroy the conveyor and have major damage to the conveyor. So any serious conveyor project really should have the conveyor dynamically modeled to make sure that you're not going to have a problem with whatever drive system you choose to run on. So just some key facts on the project. As you said, largest material handling in 40 years. We already talked about the length. So Voith worked very closely with conveyor dynamics on the design of the drive system, and Atlas purchased the drive system complete. Motor, gearbox, fluid coupling, base frame controls, the entire drive package. It was a total of 36 complete drive packages, 24 in use, and then 12 spare packages. So 21,900, 11,300, and 4 100 horsepower drives for the whole project. For the fluid coupling, a fluid coupling generates torque and a controlled acceleration by slip. It slips, and slip is heat. So we generate a lot of heat during the acceleration, but once the conveyor reaches full speed, we generate very little heat at all. But we have a program where we can model it thermally, and you'll see the red line is the temperature on the start. So the conveyor begins to run. Here's the torque of the drive. Here's the belt accelerating, and you can see the temperature profile peaks when we get to maybe 50% speed. Continue to accelerate, the temperature is already dropping very quickly. One of the operating points for the conveyor was the ability to run at creep speed, what we call creep speed for maintenance, so about 20% speed. Again, that's a high slip mode, and we have to make sure from a temperature point of view on the oil that we do not get too hot, and that was proven as well with this simulation. So, getting into the drive, back up here, there are various things we look at on the motor versus speed, torque curves, efficiency. I'll make a point on the voltage drop. So one of the reasons the project manager did not want to use frequency drives is they are very susceptible to tripping out with voltage drops. If you have a poor power supply, your grid power coming in, the voltage fluctuates, which many mines have that. They're at the end of nowhere on the grid. Experience that when you have poor power quality, you're going to have trouble with your frequency drives keeping the system running. Because as soon as it gets below about 92-93% voltage, they just give up and trip out. So this can run at 80% voltage, it doesn't care. It doesn't matter. But we look at that. So with fluid coupling, some of the things we do is look at the acceleration time. As we've talked about, how many starts an hour do they want, how many starts in direct succession, and we have to then select the appropriate cooler or heat exchanger for the coupling. In the guards, we use non-wearing metal disc style couplings so that there's zero maintenance on the connection couplings. This drive is as close to zero maintenance as you can get with all the components that we select. The gearbox has, on the bigger ones, has active cooling, so the oil temperature stays really low for a very long service life of the gearbox. And then the base frame, we designed that, and we look at all the loads. We'll get into some of the actual design engineering that goes into the base frame design. This is a point where many OEMs don't take this additional engineering steps, and it ends up being a problem once the drives are delivered and you commission them, and you end up with very high vibration levels on the drive because it was not fully engineered up front. So one of the things we first of all do everything in three-dimensional drawings. We're looking at deflection on this, so when you're applying the low-speed torque, we look at the bending of the base frame and the deflections that take place. This is the stresses in the base frames. If you can see, again, blue is nice, red is where you have higher stress levels, but on the main beam, you see there's no red area, everything looks really good. Then these are reaction forces. This is a swing-based design. It's actually supported by the pulley shaft on the gearbox, low-speed shaft, and by a torque arm in the front. Only two places. This is the point where many of these drive systems fall on their face, have a big problem. Natural frequency of the drivers. Any piece of equipment has natural frequency. So if you would hit just like a bell, when you hit a bell, it has a certain frequency that it brings. Well, base frame is the same. If you put vibration into it, it's going to respond with a certain frequency. The problem is, if the natural frequency is anywhere close to the operating frequency, you have a big problem, and that vibration could literally destroy the drive. In our first design, so this is running at 1800 RPM, which is 30 hertz. In our first design, mode 3 had a critical natural frequency at almost 29 hertz, way too close to 30 hertz. So we had to redesign, we had to make changes because that was not going to work. We went through 15 different design iterations, and if you look, here's where the torque arm originally was here, okay? Look where it is now. So we had to run several times to get the frequency response to change, and the final one now puts the third mode over the operating speed, which is fine, and more than 15% away. You want no natural frequency within 15%, of the running speed. So this was fine, but it took a lot of modeling and iterations to get it to that point. Finally, this is what the whole drive package looks like. If I could have modified this, I would have given you some pictures in that site that I took 2 weeks ago, seeing the drives. But you'll soon be able to see them if you go to the Atlas Energy site anyway. So that was the 900, the Voith inland motors, by the way. We also bought a motor company 5-6 years ago in Austria. And in this particular case, we were able to use that E-Lin. It's a Voith company. So Voith motor, Voith coupling, that's an SEW gearbox. The drive assembly is not complete without the coolers. As I said, we generate a lot of heat during acceleration, and we have very large air-to-oil coolers as part of the system. That gives you some idea of how large they are. And although these coolers are that big, once the conveyor is up and running, we actually will turn the fan off. We don't even have to run the fan because we generate very limited amount of heat at that point, and the natural convection from the coolers will be enough to run the drive. So they'll be very quiet once it's up and running, and just those will only work if you do empty creep or a start. So for 10 minutes, 10, 12 minutes they'll run, and then they'll turn off. Okay? Showing couplings. So this is the 300 horsepower drive package. We've supplied 11 of those, and this goes back to probably the couplings. Most of our mining customers are more familiar that Voith supplies constant fill fluid coupling. There's no active pump. Oil in the coupling is inside, and there's no piping, there's no controls. Very simple coupling, and if this can do the job, which in this case for these 300 horse drives it could, then this is an economical solution that Voith can offer any customer. So again, disc pack couplings, before and afters, the preferred mount arrangement, no, very forgiving for misalignment, like 6 times more forgiving than a traditional rubber flex or steel grid coupling or gear coupling. So 0 maintenance, no lubrication. So that's the 300 horse package. Just showing it with the guarding. And then we supplied 2 plus 2 spares of 100 horsepower, very similar. All these things, we're not showing you the wiring, but that big box on the end is a junction box to terminate all the instrument wires. They have instruments throughout this drive, and everything's going to be actively monitored, as I mentioned earlier. So, part of what Voith wants to offer a customer is the ability that you have a one sole source responsible for the whole drive package. We don't always supply complete drive packages, but we have the capability to do that. And by doing that, as it's highlighted there, you end up with the perfect interaction of all components. We make sure the motor is sized right, we make sure the coupling is sized right, we make sure the reducer is sized right, we make sure it all fits together, we make sure the base frame is designed right, and there won't be a problem in the field. So if there are any issues, there's just one phone call they got to make. And that is becoming more and more prevalent in the mining industry. Customers want to see just cut one purchase order and have one source of responsibility. So we're able to do that with our customer base. This is the relation with mining, Voith. So Voith's main headquarters here in Sao Paulo, and it's part of a very large Voith campus where the other divisions of Voith, paper machinery division is a big division of Voith, and our hydro turbine division. So Voith Turbo, which is the power transmission division that my colleagues and I work for, all of that's part of the same campus. And in Sao Paulo, we have very large manufacturing capability, and my colleagues actually do like vacuum pumps and repairs in the mining industry. So just a quick shout out, showing that we can support the mining business here in that area as well with those type of products and services. That concludes my part of the presentation. Any questions you might have?